So in our little journey of the atomic model, we started at the Dalton model, the indivisible model. Then we went to the Thomson model, which invalidated the Dalton model by showing the existence of the electron, and hence the atom was certainly made up of smaller bits. And then the Rutherford model invalidated the Thomson model by showing that the positive charge is actually confined to a small space we call the nucleus. And then we get to the Bohr model, which invalidates part of the Rutherford model because we know it can't just be electrons orbiting at any old random radius or distance from the nucleus. They're actually fixed. But we didn't actually fix the problem. In Bohr's model, we still have electrons going around the orbit, so they should still be undergoing circular motion and they should still be emitting EMR. So we haven't actually fixed that problem yet. So we want to actually fix that. Now, there's some things that, as I mentioned, Bohr didn't explain. So he didn't actually explain why energy is quantized and why those electrons don't emit EMR. That's what we're going to look at. His model is also only accurate for hydrogen. Once you get to helium and onwards, it's kind of crap. And he also didn't explain this whole idea of the Zeeman effect. So we're going to look at the first problem. All of these eventually got rectified within about 15 years, but our focus is strictly on the whole quantized and EMR bit. So we have to kind of go back a little bit and talk about the theory of Louis de Broglie. So to refresh your memory, Louis de Broglie proposed the idea of wave-particle duality. If we have things, for example, like light can behave both as a wave and a particle, and we talk about things that behave characteristically like waves as particles, well, why can't we treat things that are characteristically particles like waves? So for example, treating an electron like a wave. Well, that's exactly what we do in this quantum model. We've been going about it the whole wrong way. We've been treating an electron like a particle. Why don't we look at it in a wave form? So these whole regions of the quantized orbits, this comes from the idea of constructive interference. So here's our electron probability wave. Well, in orbits that this is permitted, we're going to have constructive interference. You know, the wave is going to be here, it's not going to be destroyed. So this is only going to happen at particular distances from the nucleus. If we have a region where that electron wave can exhibit constructive interference, this is a permitted orbit. Any other place, though, what's going to happen is as that wave kind of loops around, it's not going to match up. And eventually what's going to happen is you're going to have destructive interference. So this is a prohibited orbit. So if that orbit size isn't just correct, you will have destructive interference. You will not have an electron probability wave there, which means the electron can't occupy that orbit. This is exactly where the whole idea of quantization comes from. It comes from the fact that permitted orbits are areas of constructive interference and they only happen at specific distances from the nucleus. So that covers the first part. The second part, though, is the whole idea, and we're actually, sorry, I got ahead of myself a little bit. So for constructive interference, what we actually require for a condition, we know our condition for constructive interference as we've seen in Physics 20 and as we saw with Young's double slit experiment. We want some integer multiple of the wavelength. We can have 0, 1, 2, so on and so forth. But we want that distance around the orbit as well. So that distance around the orbit has to equal the condition for constructive interference. Well, the distance around the orbit, this is just the circumference. So we're going to get 2 pi times the radius of that orbit is equal to n lambda, our condition for constructive interference. So we can also substitute, instead of wavelength, we can use the Debray wavelength formula, because here we're using lambda equals h over p, which is h over mv. And then we could certainly rearrange that for, we could have this mvr equals nh divided by 2 pi. Depends on which format you'd like it in. But either way, looking at this, these conditions are the same ones that Bohr determined for the energy level of his model. So we're actually able to show that using de Broglie's theory. So that's a good thing. Now, the second part of that question is, why do the electrons not emit EMR? All right, good question. That happens to deal with the particle characteristics of electrons orbiting as particles emitting EMR. Well, if we treat the electron as a wave, waves don't accelerate. So if waves don't accelerate, they can't emit EMR. So this whole idea of emitting EMR from the electron, that only applies if we treat the electron as a particle. What we're doing instead is we are treating the electron as a wave. That's our get around for this. So instead of treating that electron as a particle, we're going to treat it as a probability wave. And that's where this all comes in. In the quantum model, unlike the other models we've looked at, we cannot precisely pinpoint where the electron is going to be. The whole idea of a probability wave is it gives us a rough idea of what chance the electron has of being there. We can pinpoint regions where the electron has a good chance of being. We can pinpoint regions where the electron does not have a good chance of being. But the thing is, we cannot definitively say the electron is going to be at position X at a certain point. All we can say is that it has a probability of being there, or a certain chance. And that's where we get into the whole wonders of quantum mechanics. Quantum mechanics is all based on the laws of probability, or this whole quantum indeterminacy. And the thing with quantum mechanics, it's a little bit stranger than what we're used to. In classical mechanics, we're very used to the whole idea that, if you have an experiment, you repeat the experiment the exact same way every single time, the results should be similar. Quantum mechanics doesn't work like that. You repeat the experiment 100 different times with the same conditions, you're going to get 100 different results. That's part of the peculiarity with quantum mechanics. It kind of messes with the brain a little bit. So let's look at some examples here. We're going to look at some examples kind of tying up the quantum model. So for us, the quantum model has been slightly refined over the years, but it is still the gold standard of our atomic model. So we'd like to compare the Debray wavelength of an electron moving at 4 times 10 to the 6 meters per second and a 50 kilogram physics student moving at 5 meters per second. Could we diffract the student? Explain. All right, let's look at the electron. So for the electron, we know the Debray wavelength is h over p, or h over mv. So we get that 6.63 times 10 to the minus 34 joule seconds. We're going to divide that by the mass of the electron. And we are told that it is traveling at 4 times 10 to the 6 meters per second. So it's going pretty fast. So let's see. What are we going to get here? So we got 9.11 times 10 to the minus 31 times 4 times 6. We're going to get about 1.8 times 10 to the minus 10 meters. So that's our wavelength for the electron, treating it like a wave. Now, could it diffract? Yeah, we're going to need we're going to need spacings that are quite small in their diffraction grading, but it can be done. Let's look at the person. So for the person, their Debray wavelength, we want that h over mv. So we have that 6.63 times 10 to the minus 34 joule seconds. This person is 50 kilograms, and they are traveling at a nice 5 meters per second. Well, they are certainly going to have some interesting phenomena. So we are going to have about 2.7 times 10 to the minus 36 meters. So a person meeting these conditions, they are going to have a Debray wavelength of about 2.7 times 10 to the minus 36 meters. So that's quite small. So for us, treating a person like a wave, you'd certainly have a wavelength, but it's so damn small that it's pretty much inconsequential. The other thing is to diffract, you need your wavelength and the spacing between the slits to be like kind of in the same ballpark. Good luck getting a slit that small. So no, we are not going to be able to diffract. No diffraction because wavelength is too small. It's way too small, so people will not be diffracted. If you throw them at a diffraction grating, nothing particularly interesting is going to happen. So we cannot diffract people. It's pretty much okay for us to treat people like particles. We do have some wave characteristics, but as I mentioned, they're kind of inconsequential. So we'd like to determine the Debray wavelength of an electron accelerated from rest across a potential difference of 600 volts. All right, so for the Debray wavelength, we know the Debray wavelength is h over p, or we have h over mv. Now, we know h, we know m, we don't know v. So we have to figure this out. But if it's accelerated from rest across a potential difference of 600 volts, here's that case here. So here's my electron. It's accelerated across this potential difference of 600 volts. So if it's going to go to this other side here, this is most likely going to be a positive plate. This is likely going to be a negative plate. So what we're going to have here is we're going to have a potential difference of 600 volts. So we talked about these questions a bit earlier in the course. We know that the change in kinetic energy is equal to the negative change of potential. So we know that half mv final squared minus half mv initial squared is equal to negative q times delta v. Right, here's where the fun kicks in. So negative q delta v, we talked about how if the electron is traveling kind of in the direction of intended motion, like if the electron's going where it would want to go to begin with, we treat that as negative work, or we treat that as negative potential. So this electron going across this gap, we'd actually say it's experiencing a potential of negative 600 volts because it's going where it wants to go. Now in this equation here, it's starting from rest, so we know that half mv squared is just going to be this negative q delta v. And we've done this many times before, so this is what our rearranged equation looks like. And again, that whole negative on the potential is going to take care of that negative there. That's why we said for these questions we actually have to be really careful with the signs. But for these type of questions here, if you forget that rule, you can kind of conveniently scratch out the negative if it causes problems. But that's more of a stopgap. That's not a real proper physics solution to the problem, but you can get away with that. It won't hurt you at the end of the day. So let's see what we're going to get here. So what we want to do is we want to find the speed of that electron as it crosses the potential gap. So as it crosses the potential gap, it's going to end up reaching a speed of about 1.45 times 10 to the 7 meters per second. So that speed as it gets across the gap, that's the speed we're going to use in our Debray wavelength formula. So what we're going to do now is calculate the Debray wavelength. So we have that 6.63 times 10 to the minus 34 joule seconds. We have that mass of, what is it? So it's electron, 9.11 times 10 to the minus 31 kilos, and then that speed that we just calculated for the electron moving across this potential difference. So what we're going to get is we're going to get about 5.01 times 10 to the minus 11 meters. So the Debray wavelength of our electron that is accelerated from rest across that potential difference of 600 volts, once it gets to that speed of 1.45 times 10 to the 7 meters per second, it will have a Debray wavelength of about 5.01 times 10 to the minus 11 meters. Right, so we have an electron. It's going to orbit a proton at a distance of 1.06 times 10 to the minus 10 meters. We're going to use the planetary model to find the speed of the electron in circular motion and the Debray wavelength of an electron as it moves around the nucleus. Alright, so we have a proton. So here's our proton. We're going to have the electron, and it's going to orbit around. So this is very similar to Physics 20 when we did those questions where you had the planets, or like say a moon orbiting a planet. This is like where we would have said that the centripetal force is provided by the force of gravity. Well, in this case, the centripetal force is going to be provided by the electrostatic attraction between this proton and the electron. So that centripetal force is going to be provided by that electrostatic interaction. Now, the centripetal force, we have mass. So what mass are we using? The electron is the actual thing undergoing circular motion. So it's going to be the mass of the electron times v squared divided by that distance between them. And then our electrostatic interaction, we know that's Coulomb's law. So we have this K, Q electron, Q proton, divided by R squared. Now, we can cancel one of the R's here. So one of those R's is going to cancel, or this R is going to cancel one of these R's. So then I'm left with V squared is K, Q electron, Q proton divided by mass. And then, of course, we can just take the square roots of this. So I'm going to get that the speed is about K, QE, QP over ME square rooted. So we know all this information. We know the Coulomb's constant, which is on the data sheet. We know the charge of an electron and the charge of a proton. They're both 1.60 times 10 to the minus 19 coulombs. And then we know the mass of our electron. So the big mistake here is not knowing what provides a centripetal force and putting the wrong mass here. Because again, when you're doing these problems of, one object orbiting around another, the object that does the orbiting, the one that's actually going in a circle, that's the mass you're going to use for the centripetal force. So let's have a look here. So we do this. We make sure we're very careful with our calculations. So I am going to get, let's see here. Is that right? I just want to make sure. Oh, whoops. Sorry. I almost forgot. I forgot the R value here. So like there's that R. That goes here as well. So, ooh, that is bad. So we also have to put that radius in there. So my apologies for that. That would have been really bad. I knew that answer didn't make a lot of sense. So let's try that one more time. So this, kiddos, is why you don't rush things. This is how I get into trouble. So let's just be really careful with that. All right. So I now have my R value, so that R goes here, and we've kept that along and brought it in. So what I'm going to get for this is that the speed of this electron as it orbits is about 1.54 times 10 to the 6 meters per second. So I've used circular motion, and I've also used Coulomb's law. So the Debray wavelength for this electron as it moves around the nucleus, well, the Debray wavelength is h over p, which is our h over mv. We know h, we know m, we just found v, so we're just kind of taking info that we have derived previously. So our electron as this mass, and then we have that speed that we just calculated. So our Debray wavelength, and again, your Debray wavelengths for subatomic particles, expect them to be small, they should not be large. So what we're going to get is we're going to get about 4.71 times 10 to the minus 10 meters. Yeah, that seems small. That seems pretty sensible. So that's going to cover us for our Debray wavelength for this electron that is orbiting this proton. All right, last piece, and then we're done the second part of this unit. So we have an electron. It's going to move around a nucleus with a speed of 3.8 times 10 to the 6 meters per second. So we'd want to find its Debray wavelength and its orbital radius if it's in the third energy level. So we've really done a lot of calculations with this Debray wavelength. So the Debray wavelength, h over p, h over mv. So this lambda equals h over p, this is in the data sheet. So that's 6.63 times 10 to the minus 34 joules seconds. We have a mass of 3.8 times 10 to this, oops, that's the speed. And then the mass, 9.11 times 10 to the minus 31 kilos. I can do MV or I can do VM, doesn't matter. Multiplying order is not order doesn't matter. So let's just do VM. Let's switch it up. So what we're going to get about 1.9 times 10 to the minus 10. Yeah, that seems about right. So then we want to find the orbital radius. So we know with the combining Bohr and de Broglie's theories, we know that the condition is that we want the circumference of the orbit, that 2 pi r, we want that to be equal to the condition for constructive interference, because we need constructive interference because that orbit has to actually exist. So we have 2 pi r equals n lambda. So at the third energy level, we're saying n is equal to 3. So r is going to be this n lambda divided by 2 pi. Well, we just found the wavelength. We're told we're in the third energy orbit, or the third energy level, so let's calculate this. Again, in the calculator, because you have two terms in the denominator, don't forget to bracket that, because we want to divide by all of 2 pi, and if I can be really careful with my calculator here, we are going to get, where is the pi button on this? We're going to get something that looks like this. So we're going to get about 9.1 times 10 to the minus 11 meters. So basically what this is saying for our nucleus, if I have my first energy level, my second, my third, don't mind my very poor drawings, what it's just saying is that electron in this third orbit that distance from the nucleus is about 9.11 or 9.1 times 10 to the minus 11 meters. And that pretty much wraps that up for De Broglie and the quantum model.